Hello and welcome to Chapter 4. Today we're going to talk about descriptive data mining, and in that we'll cover some different types of cluster analysis and some association rules between different groups, and then we'll also look at some text mining, get some definitions of what the different aspects of text mining is and how you might go about doing some text mining. So why is text mining, or not text mining, but data mining become so popular? And it goes back to what we initially talked about. It's the explosion in the amount of data that's being produced. It's coming from sensors. It's coming from different devices that is easily to grab the data off of. It's also our ability to store that data in warehouses. If you haven't had a database class, a warehouse is a group of related databases. So when we have all those different types of databases and we can link them up, then we can gather even more information and make more inquiries into what those relationships might be between the different databases. Also, because computers have gotten cheaper, now we can actually do things on the desktop that, 20, 30 years ago might have taken a mini computer or even a supercomputer. Some terms that you should be familiar with is something called an observation. And an observation is just some recorded values for variables that are associated with a single entity. And so what that means is if you've ever seen a database, that database is arranged in tables. Each table is an entity. So for us here at WKU, an entity name might be student. So within that entity, we're going to collect some information about students. So the students, information we might collect, or the variables then would be first name, last name, address, major, and so those are specific things for that student. So an observation then would be information that we collect on a particular student, and so that observation typically is going to be one row worth of data. So if we were doing this in a spreadsheet, that all the information for a particular student would be on that one row. Now, another thing you should understand is something called unsupervised learning, right? So this is a technique in descriptive data mining, and it'll help you identify relationships between those observations. You may also hear this as high-dimensional descriptive analytics. So it's a way of looking for similar patterns in the different observations that we might say, oh, these group together, and so we can group those together, and then if we had anything we wanted to do with that data, we could. For our perspective, from a business perspective, it might be, let's say we're looking at people's viewing habits through Google. We get some data on Google Analytics, and now we're going to try and say, okay, these people looked at similar things. Let's try and group these people together. And if we had a marketing campaign that we know works, then we could try it on all these people that group together in that similar, relation, that have similar relationships between those observations. Also, with this unsupervised learning, there's nothing to predict, so there's no outcome. And so you typically are going to just have qualitative assessments. Is this good or bad? And that'll be used to compare the results. Now, that may not seem like much right now, but it's a big thing. I mean, when we get into machine learning, or if you ever get into machine learning, there's supervised learning and there's unsupervised learning. So unsupervised learning is we just let the machine have the data and it runs through its algorithm and it tries to put things together. or group things. That's what we're talking about today. The next thing we're going to talk about is a technique called cluster analysis. So like I said, it's measuring the similarity between observation. And we'll just be looking at hierarchical clustering and k-means clustering. So we've got quite a few slides that deal with cluster analysis. So the goal of clustering is to group those observed variables from observation to observation. We can also use it to help reduce the amount of data that we have. So this second bullet here can be used during data preparation to identify variables or observations that can be grouped together or aggregated or removed from consideration. Sounds like a lot. An example of how I've used that in the past is, let's say we write a survey. We write a survey about questions about how students feel about different aspects of their departments within the college. So accounting, information systems, management, marketing, finance, econ. And then we do a cluster analysis on that. We can see that, okay, do these questions really group together the way we thought they were grouped together? If so, that's a good thing. And then we can also see, okay, if there are certain questions that have almost the same identical responses, then if we wanted to remove that question from our survey, we could, because we have another question that's getting a very similar or almost identical response, so there's no sense asking that again of what we're looking for. And I hope that makes sense. And then those of you that are in marketing, you may see it as a way of putting your customers into different groups. So the homogeneous is similar, and they would call that market segmentation. And once we have market segmentation, we know how we want to market to that particular group. This cluster analysis also can be used to identify outliers. So in my example of the survey, if we've got one or two questions that don't really group with any of the other types of questions that we have, we might think, well, that's not a good question. It probably should be thrown out or reworded. So the different clustering methods that we have this hierarchical clustering. So we start out by looking at one observation, so that's one record, and it belongs to its own cluster. And then we merge it with the most similar clusters to create a series of nested clusters. So we find something that's similar to that, and it's similar to something else, and so on. We keep grouping them. There's also k-means clustering, and what that means is we assign each observation to one of k clusters. So we might think we have 3 groups here, or 4 groups, and it's done in such a way that the clusters are as similar as possible. So we need to measure that similarity between observations in order to determine how similar they are. So both methods require that. So to measure that distance, we use something called the Euclidean distance. It's a fairly common method to measure the dissimilarity between observations. So let's say we have these observations. So these are measurements for the different variables. So that would be in our rows, and each column would have a different variable or field. So we have observation U and observation V, and then these would be all the different fields. And we'd have, Q variables. So that Euclidean distance, the distance between observation U and V, is we take this observation minus this V1 observation, we square that result. We sum all the results of the squared differences, and then we take the square root of that. Fairly easy to do. So here's an example. Let's say we have a financial advising company. They'd like to segment their customers into several groups. Those groups are called clusters, and the customers can be sorted within a group that are similar and dissimilar with respect to certain key characteristics. So each customer, then you have an observation of 7 variables. We want to know their age, female, income, married, children, car loan, mortgage. So here we have observation U. If we collect this information, we arrange it like this. Age 61, not female, income 57,881, married, yes, car loan, 2. I'll have to go back and see what the 2 means. And I think I got ahead of myself. It's children, then car loan is no, mortgage is no. So 0 or 1 are like dummy variables, 0 representing no, 1 representing yes. Sometimes you can use it like that. So that would be the female variable here. Car loan and mortgage are actual numeric variables. So here we have an example of that Euclidean distance. The more similar the observations are, the smaller that distance is going to be. Just keep in mind that when you use Euclidean distance, that it's very much influenced by the scale on which the variables are measured. So in order to account for that, a lot of times things are standardized using that z-score for the variable, and then the subtraction and squaring would take place. And as we've learned from the last chapter, once we have a z-score, it's easy to identify what might be an outlier if it's plus or minus 3 deviations from the mean. And what I just said is repeated on this slide here. Another thing that you should be aware of when you're clustering is that the observations, if they're categorical variables, that means they are encoded as 0 or 1, 0 meaning no, 1 typically meaning yes, they're in the category. So like female, 0 no, 1 yes. So that can cause problems. So a better measurement between 2 observations might be counting the number of variables that match those values. So you're looking at a frequency, if you will. So the simplest overlap measure is called a matching coefficient. So with that, you'd have the number of, to calculate that, you'd have the number of variables with matching values for your observations, U and V, divided by the total number of variables. Makes sense. How many of them were the same divided by a possible number. So if you got a 1 there, then that would be exactly the same. So a problem with that is that if you have 2 observations that have a 0 entry for a categorical variable, then that's counted as a sign of similarity between the 2 observations. So in order to try and avoid misstating that similarity due to not having a feature, you can calculate something called Ch4BDAN310P1 coefficient, which does not count matching 0 entries as in the following. So we've got Ch4BDAN310P1 coefficient, number of variables with matching non-zero value for observation U and V. Then to get the denominator, you take the total number of variables and you subtract out how many of them are in this categorical type for U and V. And that'll give you a better coefficient. So the example in the book of calculating both out to see how similar different observations are, they give you this example. We have this data we're collecting female, married, loan, and mortgage, yes or no, I guess here instead of amounts. And then using that similarity matrix based on the matching coefficient, we calculate that out and you get values like this. So observation 3 is very similar or 50% similar to 1 and 2. Observation 4 and 1 are 75% similar, only 25% similar for observation 2, and so on. So that's calculated out for all of them. And if you do the observation or the calculate the similarity matrix based on Ch4BDAN's coefficient, you get the following. So it's not as closely related as the previous matching coefficient, using the matching coefficient. And so looking at both of these, then you know, according to what your book is saying, it kind of depends on what the organization believes should be matching or not. And so is there a meaningful similarity if you believe that it's got females or not, or the other loans or mortgage here. And so those were, if they're dummy variables, they were taken out using Ch4BDANs or not. So then it becomes a measurement of whether you want to use this matching coefficient or the Ch4BDAN's coefficient. The next thing we want to look at is the hierarchical clustering. So it determines how similar two clusters are by considering the similarity between the observations that make up the cluster. So initially you start with an observation in its own cluster, and then it goes through an algorithm that combines the two clusters that are most similar into a single cluster. So this gives us a way to measure similarity between our observations. So there are different methods that you can use as you're combining these into one cluster. So the different ways you can do this is through a single linkage. And so the similarity between two clusters then is defined by the similarity of the pair of observations that are most similar between the two clusters or groups. There's complete linkage. This one defines similarity between two clusters as the similarity of the pair of observations that are most different. So you're actually taking and moving them to a different group. You could also do a group average or linkage. So this defines the similarity between two clusters to be the average similarity computed over all the pairs of observations between the two clusters. So which group average is similar to another group average. We could also do the same thing if we were looking for a median linkage. So it's very similar, but now we're looking for the median. So the between all pairs of observations between the two clusters. And then we can also do something called a centroid linkage. And this uses the averaging concept of cluster centroids to define between cluster similarity. I'm going to go back and say something else about the complete linkage. And so when you use complete linkage, they're looking for the dissimilar pairs between the groups, and they say that the groups are most similar if they have the least amount of dissimilarity between them. So let me say that, you know, to consider two clusters to be close, then they're looking for their most different pair of observations to be close to each other. So you're saying, okay, in this group and this group, and we're saying what are the two furthest apart observations from each of the groups. And if they're very close together, that's going to have a small measurement there. So that was what we mean by the complete linkage. So if we look at this graph here, that complete linkage, we have 1 here and a 6 here. That's the furthest difference apart that they can have. That centroid, like I was saying, is a calculation of what is the centroid measure for this group versus the centroid measure for this group. If they're very close to each other, then we would group those. We can also do an average here, and you'd see getting an average of the differences, or those distances, I should say. And then that single linkage, the ones that are most closely together. So 3 and 4, there's only a difference of 1 there. Can we get anything else as a difference of 1? No. Some other methods that you may hear about, one is Ward's method. It merges 2 clusters such that the dissimilarity of the observations with the resulting single cluster increases as little as possible. So the dissimilarity, again, we're looking for a small distance between the 2 clusters. When we group them together, then there shouldn't be much of a difference in there. We have McQuitty's method, considers merging 2 clusters. The dissimilarity of the resulting cluster AB to any other cluster C is calculated as the dissimilarity between A and C and the dissimilarity between B and C divided by 2. So we put 2 together, then we say, okay, how different is that group from another cluster? So we take out A and then measure that dissimilarity, however we're doing that, with C, and then add that to the dissimilarity to what was B, and then get an average, so dividing by 2. And we can depict these things in something called a dendrogram. So it depicts the nested clusters and how we're grouping them at each step of the aggregation. So look at this grouping that we have here in this slide, or dendrogram. So you need to follow along in your book if I'm not explaining it slow enough, but it's fairly easy to figure out. So we have 1 cluster here. So this represents a cluster. So we got observation 4, 5, 6, 11, 19, 28 combined with 1 here. Right, and so then we combine that with this value here, which is another grouping of 7, 21, 22, 29, and 30. And that represents that grouping of all of these observations. So if we back up a little bit, we see that we have 1 cluster here. We have another cluster here, so 1 is out there by itself. When we group those together, it has a dissimilarity of around 0.25. And then if we look at this cluster, cluster 7, and then we combine that with this cluster here, it has a dissimilarity of about 0.25 also. Then combining these 4 clusters together, we have a dissimilarity of about 0.33 maybe. And that process just continues there for the other observations that you have. So this diagram is useful for identifying clusters that you can see would be combined, and then you can say, okay, what's in those clusters? Is this really a good combining or not, or do I want to keep them separate? And then from there, you could use your clusters to do whatever initial analysis you wanted to do. What does this group do that's different from another group? Another thing that should be pointed out is the length of the line here, this vertical line, determines the strength or durability of the cluster. So the longer the line, the more unique that cluster is before it's being combined with some other cluster. So if you were looking at, observations 12, 24, and 29, that might be a group that you want to single out for your analysis later on. And I'm going to pause there, and then we'll pick it up with k-means clustering when we come back.